Hello, friends! A very warm welcome to today's explainer. Nadi here. Today we are taking a concept that sounds honestly terribly complicated, algorithms, and we're going to reveal it as a beautifully simple trick. So, let's open up Nadi's Guide to Binary Search.
Okay, imagine a massive warehouse. It is literally filled with millions of building blocks. Now, what if I asked you to find one very specific block in all of that? Say the block with the exact size of 10. Are you really going to check every single block one by one? Oh, no. That would take hours, maybe even days. We absolutely need a smarter way to search. So the question becomes, how do we find one specific block in a massive pile very quickly without losing our minds?
Well, I am saying to you, hello friends, kindly pay attention as we do the needful to find our missing block. We're going to use a truly brilliant trick from the world of computer science. It's actually the exact same trick computers use all the time when they have to search through millions of files. And you know the best part? We are going to understand it completely, just by thinking about our simple block puzzle. Absolutely no heavy mathematics required, just pure, beautiful logic.
Now, the formal definition of binary search is that it's a fast algorithm that finds a target by repeatedly dividing a sorted list in half. I know. Algorithm sounds like a very heavy word, doesn't it? But really, an algorithm is just a recipe. It's just a set of instructions. And binary, that just means two parts. So we're simply taking our pile of blocks and cutting it in two, again and again. It's a first-class method for sorting through our puzzle, and it's going to save us a tremendous amount of time and energy. But wait, before we do anything, we have to talk about the golden rule, sorting first. Let's look at our starting point. We've got 3 blocks here, sizes 10, 20, and 30. And notice how they are standing perfectly in line, going straight from the smallest to the largest. This ascending order is strictly necessary, isn't it? If they aren't sorted exactly like this, we simply cannot use our clever trick. The entire system completely relies on us knowing exactly where the small things are and where the big things are. So, rule number 1, always sort the blocks before searching. Please kindly keep this in your mind. If the blocks are all jumbled up, say 30 is sitting right next to 10 and 20 is wandering off at the very end, this algorithm simply will not work. It will give you the wrong answer entirely. So remember, first we sort, then we search.
All right, let's move on to the actual secret, splitting the blocks.
Here is our foolproof recipe. Step 1, we find the exact middle block of our line. Step 2, we look at this middle block and compare it to the one we're actually searching for, our target. And step 3, based on that comparison, we just throw away half of the blocks. Yes, you heard me correctly. We discard an entire half that we know is cent% wrong. Just think about how incredibly powerful that is. Imagine the time we're saving instantly.
Let's put this into practice right now. Our target today is block size 10, and we are looking for it among our neatly arranged blocks of sizes 10, 20, and 30. Sure, it's a very small example, but I promise you the logic scales perfectly, even if we had 10,000 blocks.
So we have to make a decision, left or right.
Out of 10, 20, and 30, the middle block is clearly 20. We put our finger right there on block 20. Now, I ask you to kindly think about this. Is our target smaller or larger than that middle block? Well, our target is 10. The middle block is 20. 10 is obviously less than 20. And because our blocks are perfectly sorted from smallest to largest, we know for a cent% fact that all blocks to the right of 20 are even bigger. They're 30, 40, 50, and so on, which means they're absolutely useless to us.
Because our target 10 is smaller than the middle block 20, we simply don't need that right side anymore. We discard it completely. Just toss it out. Notice how the blocks we kept now only consist of size 10. The discarded blocks, 20 and 30, are totally gone. We eliminated them without even having to check block 30 individually. Now that is the pure magic of splitting things in half. And that brings us to the final match. We now have 100% focus on the final remaining block. Think about it. After just one single split in our puzzle, we only have one block left on the left side. What is the middle of one block? Well, it's just that block itself. So we direct our full attention right there.
We compare it to our target. The remaining block is size 10. Our target is size 10. Do they match? Yes, target found. We did the needful perfectly, and we did it so incredibly fast. We didn't have to touch every single block. We simply let that sorted order do all the heavy lifting for us.
Now, I want you to consider this single number, 20. You might be thinking, Nadi, my friend, checking 3 blocks is easy anyway. What's the big deal? But what if you had a massive warehouse with 1 million blocks? If you check them one by one from start to finish, it could literally take a million steps. But with binary search, by cutting the pile in half, then in half again and again, it would take you at most 20 steps to find your target among 1 million blocks. Just 20. That insight is absolutely brilliant. It proves just how immensely efficient this algorithm truly is when you are dealing with massive data sets.
So the absolutely crucial takeaway today is that sorting your data allows you to search it with lightning speed. It turns seemingly impossible tasks into simple ones, which leaves us with a wonderful question to ponder. What other massive puzzles can we solve using this clever splitting trick? Whether it's finding a contact in your phone book, a supercomputer searching a global database, or even just organizing your own daily life, dividing the problem in half is a powerful first-class tool. Thank you so much for joining me for this explainer, friends. Keep exploring, keep questioning, and I will see you next time.